Hello, so this is the XFOIL project for Fundamentals of Aerodynamics. My name is Henry Bright, and I'm going to walk through the three parts of this project. So basically, we have part one, where we're going to compare three different airfoils, part two, where we will compare three different Reynolds numbers, including inviscid flow for the Clark W airfoil, and then also for the Clark airfoil, part three is going to be adding flaps at two different deflections. So we're going to go ahead and go through that. Let me go ahead and share my screen to show you XFOIL. So you can see my tabs here. I have a folder made for the projects. That's where all our files are going to go to. But if we just open up the XFOIL app, and then I share that screen for you. Here we go. We are in XFOIL now. So you can see these are the options that I'll pull up. So the first thing we're going to do part one is we're going to do the three different airfoils. The first one I'll show you is I'll just show you how we do the NACA airfoil. So we'll do the 2415 just to show that as an example. So if you just type in NACA and then 2415, it pulls that up. And if I show you the other screen in just a second, actually, we'll be able to view that. So if we go to XFOIL here, anyway, so you can see we have our parameters. If I open up PPAR, that's going to allow us to change some of the parameters of the airfoil. And if I share it as well here, this is what you'll see. So you can see it's got the number of panels and max panel angle. So you can kind of see each of the panels along the airfoil surface there. But that's our NACA 2415. So if I come back to XFOIL, I'll show you what we're looking at. So it asks you to change different options. So the first one is we'll change the panel nodes. We're going to go with 250, should be a fine number. And then the trailing edge to leading edge panel density ratio, it's currently at 0.15. We're going to want that at 1. And then if we hit enter again, that resets all those settings. And if we go back to the airfoil, this is what we see. And you can see the paneling nodes have been updated. So that is good for us. So if we come back here, we'll hit enter again to clear out of that. And now we're back in XFOIL, you can see. So the next thing that we need to do is we're going to need to be able to choose our flow. So if we go to OPER, O-P-E-R, operation, you can see it says OPER I. That means it's dealing with inviscid, so that's the default flow. For part one, we're going to be doing viscous flow. So we type VICS, or VISC, sorry. And then it's going to prompt us to enter a Reynolds number for this project. We're going to do 1 million, get enough zeros there. And so we've got our Reynolds number in there. And the other thing we need to adjust is our iteration limit. So we're going to go ITER, iter. It's currently at 10, so we're going to need to increase that. We're going to go to 1,000 just to be safe. Most likely we won't need that many, and it should converge before that. Okay, so once we have this set up, the next thing we can do is we're going to run what we need. So the first thing we want to do is we're going to want to save to a file. So I'm going to explain how to do this just this one time. Is we'll do PACC. So that's going to help us create a polar file, save file. So it's asking for the file save name. So we're going to do just example. I don't want to confuse this with the rest of my file names. We don't need a dump file name. So we hit enter again, and we've got polar accumulation enabled. You can see it's OPER VA, so accumulate is on. So now we're ready to save the data that we get. So to do this project, we're going to need to do a sequence of alpha angles is what we're going to change because we are getting our data for varying angles of attack. So for this one, we're going to be doing from negative 15 degrees to 5 degrees, and we're doing a 1 degree increment. So we do ASEQ, ASEQ, sorry, space, and then we do -5. So that's our low limit, and then our upper limit is 15, and then space again is 1. So that's the degree that it's changing by. So if we go ahead and hit enter, it's going to start running these calculations. You can see everything's converging fairly quickly. You can see the numbers aren't accumulating too much. It's just getting each of these angles of attack. And then once we get that, boom, that is good. I will share you my other screen of the plots. And there you go. You can see it. So we've got our CP distribution. So you can see it varying for different angles of attack. Each of these lines is. You can see the airfoil here. So you kind of see from basically from C equals 0 to C equals 1, the chord length. You can see where the graph is varying. And then it also gives you a plot table of your angle of attack, lift coefficient, drag coefficient, all of that fun stuff. However, the other thing we did is by saving that file, which is when we did the PACC command, we're also going to be able to see the data that we get. So if I show you my folder, it's going to give it in the same folder where I have XFOIL. You can see it created an example file. So what we can do is go into Excel. So I'm going to go ahead and share my screen for Excel. And you can see this is already the data that I already collected. So basically, this is what it gives you is once you convert it, you have to go, I'll actually show this process just for this one time. If we go to open and then browse, and we find our example, make sure you change this to all files. Mine is already pulled up that way, but you go to open. It says it doesn't match, but we're going to make it match essentially so that it creates it in the columns we want. We just go next and next, and then finish. Don't have to change anything there. You can see the formatting gets a little messed up because again, it's not in Excel format. But you can see it gives us all that data. So that's the same tabulations that were on the plot that we saw in XFOIL. It's from -5 degrees to 15 degrees alpha. And so from there, what we can do is I'll show you again. Oh, I'm so sorry. I was not showing you the example slide. Here we go. This is what the example looks like. So sorry. I did not change the share screen. So this is what it looks like. It goes from -5 to 15. It's the same as what's in that other Excel folder or Excel document. I'll go back to that one because that has the data that I've already calculated. I'm not going to bother going through all of that because basically what we can do is when we pull this up, we can go to insert and we can do a new scatter plot. If we do this one, and then you can right click, select data. And so then from there, you can add a series. And so for each of these, basically I ran it already for the NACA 0015, NACA 2415, and the Clark W airfoil. And so we already have our data for those. And so then you can just title it with whatever series you want. So you can see I did the ones for the 3 different airfoils. And then the X values would be your alpha, and Y values, which would be whatever coefficient you're looking at. So like lift coefficient, you would do that whole column. And that's how we would put that in. So I'm not going to bother actually doing that because I don't want to waste that time. But you can see this is what it comes out to. So you've got your lift coefficient versus angle of attack, drag coefficient versus angle of attack, and our aerodynamic performance, which is lift coefficient over drag coefficient. And you can see the different values for the different type of airfoils. So you can see I have all the values that I had copied in from XFOIL from those Excel sheets. And then you can also use Excel by highlighting the whole column. Then you can get the max. You can set a formula for max value. So this was the max lift coefficient, and this was the minimum drag coefficient. So we have all of that capability in Excel, which helps us. So that is part 1. I will explain that. Part 2, or I have explained that. Part 2, we're going to come back to XFOIL. We're actually going to close XFOIL, and I will keep it on Excel for a second. We're going to close XFOIL. Part 2, this is a little taste of the results we're going to get, but what I have to show you, we had to do this for part 1 as well, but we also have to do it for part 2, is we're going to have to load our Clark airfoil. So to do this, basically, we go to the UIUC airfoil database, which I believe I actually have pulled up. I just need to find it. Yeah, okay, I do, and I will share that. UIUC airfoil data site. So you can see at the top, this is what it looks like. And so it's an airfoil coordinate database. So it has the coordinates already plugged in into a compatible format for XFOIL, or we will be able to make it compatible, I should say. But it's got basically all the X and Y coordinates to form each of these airfoils. So basically, if we go to C, we're going to find the Clark W DAT file. That's the file we're going to want to get. So you'll download that file. Another pro tip that I will give is if you go to the zip archive of these files, it's going to have every one of these in there, but that's okay because you can go through and find the Clark W airfoil on there. And once you get that one pulled up, it actually has the coordinates in the correct format. So basically what we need is we need the coordinates to go from the trailing edge to the upper surface, so all the way around the upper surface, and that leads to the leading edge. And then from the leading edge on the lower surface, it goes from the lower surface back to the trailing edge. So that's the way we need the coordinates. And so basically we'll start with like a x=1 coordinate. You're starting at the trailing edge, and you'll come all the way back around that 1 from the top surface and then to the bottom surface. So that's a pro tip. Otherwise, you can just download the Clark one from the UIC database here. And there it is. And then if you click on it, actually, it'll show it to us. There's the coordinates. You can see it starts with zeros, 0, x, and y. So this would start from the leading edge, which we don't want. We want it to start from the trailing edge. So we would want to start it from here, go upward through these values, and then go down through these values and go along from the leading edge to the trailing edge on the lower surface. So that's the format that XFOIL will satisfy. Like I said, I already took care of that. So I already have a file in my XFOIL folder. It's Clark W, and there's the DAT file, and it already looks like it should. I think I will open Notepad here. If I show you the screen in Notepad, there it is. And see, it starts from 1, or x=1, y=0, so starting from the trailing edge, and that's the proper way to start, and then comes back around to the leading edge, and then back to the trailing edge. So that's what we want. So that being said, we're going to come back to XFOIL. We already have that that file in place. So basically all we need to do, it's very simple in XFOIL, is once we have that file and it's properly formatted, we'll put in load, and then you need to name the file exactly on here. So clarkw.dat has to be exactly right for it to load. And sure enough, it does. And it'll pop up on your screen with this screen. And you can see current airfoil paneling. That's exactly what it looks like. So this is well done. We are in good shape. So we'll come back to the XFOIL command window here. And basically what we need to do is we need to do the same steps that we did for the last time, which I will run through really quickly. So we'll do our PPAR, and we'll change again nodes to 250, that ratio, panel ratio, density ratio to 1, enter again, and we're back into XFOIL. And you can see again, I'll share that this is what it looks like. So you can see the paneling nodes have been updated as we wished. Come back to XFOIL. Okay, and then again, OPER. And this time for part 2, we're doing inviscid flow, laminar flow, and turbulent flow. So the difference is, like I said, OPER automatically opens the inviscid flow. So for that case, we're just going to use that, and we're going to go ahead and proceed with, we'll do our save accumulation, so our PACC. We'll have to update our iterations again to 1000, and then you'll be able to go ahead and run the ASEC to get the alpha sequence from -5 to 15 again with a 1 degree increase each time. So we could go ahead and do that. Or if we need to do like the laminar, we already have the turbulent case done because this is for the Clark airfoil. But for the viscous flow case, for the laminar case, sorry, you'll have to change the Reynolds number to 300,000. So that is in place as well. I'll go ahead and run, just for completeness sake, we'll go ahead and run the inviscid case. I'm not going to save this. I'll just go ahead and do the ASEC. 5, 15, and 1. And it calculates it basically immediately, which is pretty cool. So if I share this screen, you can see I was waiting for it to do something, but it actually had already done it. And that's what it looks like. You can also change the CP min. If I come back to XFOIL, sorry. Back to XFOIL. If we do CP min, you can see it says current is -2. Let's increase that to -6. And if we come back, we're going to go ahead and run the ASEC again. It's -5, 15, 1. And then if I come back to the share, you'll see a little bit better because you can see it was cut off a little bit, and it still is. It still could go a little higher. But again, you got to remember this is also the inviscid case, so it's a little bit different. But anyway, yes. And then if we come to our spreadsheet, I'll show you again. This is part 2. So again, you'll get that data saved with the data accumulation, and then you can plot the 3 plots that we need. So lift coefficient versus angle of attack, drag coefficient versus angle of attack, and the aerodynamic performance versus angle of attack. And you can see that I have the laminar and turbulent cases listed here. So that gives us all of our data for that. And that's basically how you do part 2. So the last but not least is part 3. And so if we go to part 3, I'm going to share this again just to remind myself. Part 3 is the flaps. So I'm going to show you how to add flaps. So let me open XFOIL again. Just as a reminder, basically XFOIL is a program that you can open one time and you can close it immediately and open it right back up to like restart. That's kind of a good way to go about it. So that's what I'm going to go ahead and do. So I will share XFOIL again. Here we go. Now that I've reopened it, we'll go ahead and load our Clark W DAT file as we did last time. Again, panel, the diagram of the airfoil pops up in the other window, but I'm not going to show that again. So what we're going to do is geometric design. The code is GDES. And then it's going to pull up automatically this other window, which I'm going to show you, with a look at the airfoil and some statistics on it with thickness, camber, and such. But if I come back to XFOIL, this is where we're going to manipulate this to add the flaps. So it's very easy. We just do flap, and it's going to give us some options that we have to input. So we need the X location of the flap. So going from along the chord length, this chord in this case, we loaded this airfoil, it goes from 0 to 1. So the X location, we're just going to choose 0.7. Just as an example, that's what I did in this project. And the next thing we're going to do is we're going to do the thickness, based on the thickness ratio of the airfoil, we want to specify the Y location. So to do it by thickness ratio, which you can see Y over T, we're going to type 999. And then it's asking us for that relative Y over T location. And we're just going to want it halfway relative, so 0.5. And then the last thing we need to do is flap deflection in degrees. Again, it says plus is down. So plus will, if we do like plus 10 degrees, that's going to tilt it down. So that's what we're going to do for this example is we'll just do 10. So that means it's going to go 10 degrees down. And then the last step that's very important is execute, EXEC. We need to enter that code, and we can go ahead and enter to get out of GDES. And so I'm going to show you, this is what our screen is going to look like on the popped up window that I showed before. So you can see the purple is showing you where that flap has been added versus the white was the original airfoil. You can see that flap has been added. So that's exactly what we wanted. Perfect. So I'll come back to XFOIL and go ahead and show you the remainder of how this is going to look. So we're going to do basically the same as we've done before. We'll do PPAR. We're going to do N. I've done 350. Sometimes you need a few more nodes to get this to converge. Our thickness density rate, panel density ratio is 1 again, and that looks good. We'll enter again. We'll go back to OPER. We want to do a viscous flow, and we're going to go back to our Reynolds number of 1 million. So that looks good. And then again, we're going to run. You would do the, we need to change the iteration limit. We'll go up to 1,000 again. Normally we would do the PACC to save and do save accumulation. I'm not going to bother doing that because I don't want the file saved again because I already have all the data. But basically we'll do ASEC -5, 15, 1 again. And you can see it goes through its iterations. Might take a second here to converge. But once it does, as it does, it's going to automatically generate that CP plot. You can't see it right this second the way I have this shared, but I will show you that plot in a second. It's going to automatically generate that as it's iterating. So this may take a second, but basically I'll be able to show you the final result. While it's doing that, I can actually show you the plot and it generating essentially in real time. You can see it's adding the angles it's already gotten from -5 to 1 degree angle of attack. And it's going to just automatically generate these as it iterates. Each of these steps may take a different length of time. You can actually go in, and if you do ALFA in the command window of XFOIL, you can actually do it for specific angles of attack. This is just a sequence that we do to get all of these values that we want, all the different angles of attack, so we get a comparison. But you could do this and just get a value for one of the angles of attack. So we'll continue waiting on this to iterate. While it does, actually, I'll go ahead and show you the Excel so we don't waste any more time. I'll show you what the Excel looks like for part 3. This is all the data that I got. So we compared the no flaps. Again, this was the turbulent case, basically we're pulling from with the Clark W airfoil, so the Reynolds number of 1 million. So we got the same for that. We have our flaps at 10 degree 10 degree deflection downward, and our flaps at 20 degree deflection downward. So it's interesting to see the data when you plot all of these, as I showed you before. You have, again, your lift coefficient versus angle of attack, drag coefficient versus angle of attack, and our aerodynamic performance versus angle of attack. So it's interesting, you can see the aerodynamic performance is greatest with the 10-degree flap, so not too intense of a flap deflection, and at low angles of attack, because as we increase the angle of attack, we're going to steadily get very quick increase in our drag coefficient, which you can see here for both of them. We're going to get a really high drag coefficient because basically when we start to make it at that high angle, we're getting even more of a blunt body, essentially. And with that blunt body, we're going to have an increase in pressure drag. And that's going to be a major issue because our lift curve slope, again, is not diminishing too much at those high angles of attack, just a little bit. But we're going to have our big issue is going to be drag, the steep increase in drag. So if I go back to XFOIL, let's see if it's done. It is done iterating. So you'll see this is what our command window looks like. It finally got through all of its iterations. And if we go to the plots, there's that. And you can see it overlays it, so it makes it a little messy, but basically gives us what we need. And going from angle of attack -5 to 15 degrees in the flap, you can kind of see how the design looks. So that's pretty cool. And again, I think that was everything on Excel. That should take care of you. Just got to get those like maximum and minimum values where needed with like minimum drag coefficient, maximum lift coefficient, all that fun stuff. So yeah, that should complete our discussion on this XFOIL project.